Exponential growth, we've looked at a few times. We've never called it exponential growth. We've never referred to it as a graph, even though you've seen it as a graph once or twice. Exponential growth, a good example is compound interest when you put money in the bank. Okay, we've talked about the fact that an exponent or an exponential graph is in the form y equals ax, y being the dependent variable, x being the independent variable. Now, when we've looked at it as compound interest, we actually had the compound interest formula that we looked at, and it was a equals p outside of 1 plus r to the power of n. Okay, that's the compound interest formula. You will have seen that. You should, I hope, recognize it. Okay, if you think about it, if you had any percentage, any interest rate, we're always adding 1 to it because it's increasing, correct? So that is the equivalent of that little a in front of the x. The n is the independent variable. Time is independent. The amount is the dependent variable. Okay, so what we've got is if I had instead of the y, I've got an a, instead of the x, I've got an n. Cool? And instead of the little a, which I'll have to write down here for now, I've got the 1 plus r. Okay, they're what replaced. So we've got the y equals a to the power of x. In the compound interest formula, they're the equivalent things. Now, the number out the front, the p, is just a number that you're multiplying it by. In fact, it's like we sometimes refer to it as b, because you can have it in the form of y equals b a x, which is exactly the same thing, but you've just got it times by another number. In this case, the p, principal. Everyone happy with that? Just so you can see that it does relate back to the exponential. It is in the same form as that exponential graph that we've written on the board there. Yeah? Okay. I'll just get rid of these now so that it doesn't get too confusing. Whee! Or any more confusing, because we don't want that. All right. Sorry, what's up? Okay. All right, so in this particular example, Glenn invests $10,000 at 8% per annum with interest compounded annually. The growth of this investment can be given by the exponential function. A equals P, so his principal was 10,000, the initial amount. 1.08, that's the 1 plus R. Happy with that? Because the R would be 0.08. 1 plus R would be 1.08. Okay? And then the N is the number of years. Now, they haven't given us a number of years yet. What they've said is that graph the growth of this investment. So what we're given is a range of N's, and we're going to fill in that table of values, and then we're going to graph it and see what it looks like. Okay, but you can see from the function that it is in the form y equals b times ax. Happy with that? So I'll give you about 30 seconds or so to fill in the table of values. All right, guys, so up on the board, we've actually filled in the figures. I know they're a bit hard to read, but hey, you can actually do it yourself. On the calculator display, you can see how I've put it in. The only thing that changed was the 1 changes, because that was the n. Do it with the 1, then you do it with the 2, 3, 4, 5, 6, 7, 8, 9, 10. Now that we've got those values, we actually have to plot the graph. One of the problems you have is these numbers aren't pretty. They're not pretty numbers. So when you go to plot them, it's going to be very difficult to have it exact, because the scale that we're using, if you can see, we're going up by 5,000 each time. So getting the scale exact is not going to be easy. But what you can start off with is number 1 starts at 10,800. Oh, question. What would it be at time equals 0? 1. It would be, but remember this would be 1, the exponential part of it. That would be 1, but then you've got to times it by the 10,000. So what would your initial value, your principal be? 10,000. So we're actually going to start at that point there. Okay, it's very important that you remember how that works. Okay, any exponential is going to start at 1, but then it's times by that b value, which in this case is the principal, which is 10,000. So 1 times 10,000 is 10,000. All right, and then you just go across and keep going. So 1 should be 11,664. And like I said, it's not going to be precise because our scale is a bit too small. Once you get 2597, you know that goes up. Each line is 2,500. Sorry, mate? lever. 14,693. So this is not going to be perfect by any stretch. In fact, it looks hideous. Hang on. Hang on, he said. Okay, let's have a look. 10,800. Oh, I missed the first one. I wondered what you were talking about. No, you're an idiot, sir. Hang on. Oh, wow. These lines aren't very good because there's only 3 lines there. So that'll be 1, 2, 3. That'll be 4. Wow, that's worse. I'm going to do this. Wow. No. What we do, go to 5, do 5s. So that's 14,693. So that's about there. Then we'll go to 10. 10 is 21,589. So we're talking about there. Then we come back, do 2. So just to the left of this line here. Actually, I'll do 3 because it's 25. So it's about there. Then I'll do 8, which will be about there. That's better. So what you actually get is that. Yeah. I'd put the 5 in and put the 10 in and then just try and graph it like that. That's weird. Yeah, they didn't allow enough spaces there. That's annoying. No wonder it looks so weird. 21,589. All right. So is everyone happy about that? That was a bit of an awkward one because they hadn't drawn the scale very well on the bottom. But is everyone happy with the process? You're substituting in, and then you're just plotting your ordered pairs. Yeah, beautiful.